let's continue. So we had a fourth lecture of Akihiro.
Okay. So there was one small correction. Shouldn't have made such a mistake. It's just a first year linear algebra, how to express linear transformation in matrix form. The way they could have done is that A times some basis matrix, the matrix representation of a linear transformation. A is determined by AU times U some matrix, and this matrix is called the metric representation. Yeah. So I wrote U on the other side. So and then you move this unitary matrix on the other side, and you get U star AU. That's the diagonal, the block diagonalization. Okay, so what did we discuss in the previous lecture? In the previous lecture, we discussed the structure of the adjacency algebra of association scheme over the complex number field. And using the property that it is a star algebra, it is closed under star operation that allows one to decompose the standard module into orthogonal direct sum. And that allows one to block diagonalize the algebra. And the same is true for the algebra of representation, and from that I proved the double centralizer theorem. Now, in this lecture, I will mainly focus on the multiplicity-free case, that is this repetition, not the repetition, but in the centralizer algebra is of this form, the full matrix algebra repeated mi times, and the multiplicity-free means that the centralizer algebra is commutative. That occurs precisely when each of this block has size 1. So if this matrix algebra is one-dimensional, you just have a scalar matrix of size mi on the diagonal. And that is the structure of the commutative adjacency algebra. The consequence of this, this fact can be proved without using any abstract algebra, because if the adjacency algebra is commutative, then it consists of pairwise commuting normal matrices. Then it is just a linear elementary fact in linear algebra that the set of pairwise commuting normal matrices can be simultaneously diagonalized. So the abstract theory I mentioned just reduced to this elementary fact in the commutative case. I think I need to erase this equality. So in this case, the adjacency algebra is isomorphic to the R copy. So this R is the number of blocks of scalar matrices, so this I runs through 1 to R. But then, if we know this abstract structure of this commutative algebra, then it's just like the algebra of vectors with component-wise multiplication. So you have the unit vector, and the unit vectors in the right-hand side is denoted by E sub I on the left-hand side. So they have a property that the product is 0 if the indices are different, and the square is itself. So this is such a basis of the algebra, which is isomorphic to our copy of C, is uniquely determined. Okay, so how does this space look like? Well, after block diagonalization, well, originally I had U star AU on the left-hand side, but I moved U on the right-hand side so that A is equal to U times this commutative diagonal algebra U star. So the position of star is different. But this has a basis of primitive idempotence. That is, you just take out this scalar, then you get a single matrix where you have 0 and 1 on the diagonal sandwiched by this unitary matrix. This is the basis of this algebra. It has a property that they are mutually orthogonal in the sense that the product is 0 if you have different indices ij, because then the position of diagonal ones are disjoint. And square is itself because it's 0, 1 matrix sandwiched by this unitary matrix. And moreover, this matrix is Hermitian because you have a diagonal 0, 1 matrix, which is obviously Hermitian. It is real symmetric, but if you sandwich by the unitary matrix, you get the Hermitian matrix. I will use this fact later, that the primitive idempotents are Hermitian. But then, you know, there are many idempotent, well, not so many idempotent, there are only finitely many of them. You can express all idempotents in this algebra, because if you have an idempotent, then certainly you can express in terms of a linear combinational basis, but we know exactly how a basis behaves with respect to multiplication. So every idempotent is a linear combination of the basis, which are, again, idempotents, but the scalar must be 0 and 1 in order for this E to become an idempotent. So every idempotent is the sum of some of these primitive idempotents. And moreover, the rank of E is just the sum of the rank of these primitive idempotents. Because if you take the sum of these primitive idempotents, you get the 1 in this joint position. The rank is the number of ones on the diagonal, but this 1 appears in this joint position. So the rank of the sum of these idempotents is the rank, sum of the rank of the primitive ones. Well, this gives one particular idempotent. In the axiom of association scheme, the set of all says that set of all relations partitions the direct product omega times omega. So that translates in terms of metrics. The sum of all adjacency metrics is the O1 matrix. So in particular, this O1 matrix belongs to the adjacency algebra. But if you divide by the O1 matrix by its size, then it becomes the idempotent. If you square this, then you get the row sum of this of J, which is this denominator. So the square is again the same matrix. So this is one of the idempotents of the algebra, but so it is expressed as a linear combination of primitive idempotent, but this matrix is rank 1. So there is no way to express as a linear combination of more than one idempotent. So it must be equal to a single idempotent. So let us call that particular single idempotent E sub 0. Well, originally I indexed the idempotents by numbers from 1 to R, but it's customary to distinguish this particular idempotent by the number 0. So I now have a D plus 1 primitive idempotent instead of R. Sometimes in the theory of association scheme, this D is referred to as a class, and the D plus 1, which I previously denoted by R, as a rank. So these two numbers essentially same, they differ by 1. So primitive idempotents are basis. So this is a basis, but one of the basis element is this normalized O1 matrix. Now, adjacency matrices form a basis of an association of the adjacency algebra. So we now have two different bases. One consists of adjacency matrices, and one of the adjacency matrices is the identity matrix, so I will write this as 0, and the dimension of the algebra was d plus 1, so the rest of the adjacency matrices are denoted by A1 to AD. So we have two bases, so there is a matrix which transforms one basis to another. So we have A0 to AD transformed to E0 to ED by some square matrix of size d plus 1 by d plus 1. It's a little bit strange that if you think that they are matrices of big size, but forget the fact that they are matrices, but just some element in vector space. Then this is like a d plus a row vector of size d plus 1, so you can multiply this row vector with d plus 1 matrix, so you get this. In other words, a more straightforward way of expressing this linear relation is that the jth column of this vector, that is the jth adjacency matrix, is a linear combination of these, whose coefficients are just the jth column of P, that is Pij, where the sum is from sum is for I from 0 to D. That's the linear combination. So primitive idempotence is a basis, so you can express the adjacency matrix in terms of primitive idempotence. Then, because primitive idempotents are very convenient for the ordinary multiplication, because it's just zero if they are different, so you can easily compute the product of two adjacency matrices. If you have two such adjacency matrices, you just multiply, just like component-wise, the coefficients. Because of this rule, you just get the product of coefficients. So, in a sense, this is very similar to the entry-wise product, because it's the coefficients are multiplied component-wise. In other words, we have an expression of adjacency matrices in terms of column vectors of P. And column vectors are multiplied component-wise when you multiply adjacency matrices. So the multiplication in the adjacent algebra written with respect to the basis of adjacency matrices is the same as entry-wise product of column vectors of P, because column vector expresses adjacency matrices. So this is how we understand the commutative algebra of adjacency matrices. But the entry-wise product reminds us of another operation which I defined earlier, that it's called the Schur-Hadamard product of matrices. So it is just the entry-wise product of matrices. So if x and y are matrices of the same size, you just multiply entry, and that is denoted by x circle y, not the ordinary product. It's some strange product, but this is not that strange if you consider adjacency matrices, because they have ones in disjoint position. So if you multiply ai and aj with different indexes, you have 0, and otherwise you have the same matrix, ai. So this behaves almost like primitive idempotence. So you have two different bases, and they behave quite differently in terms of ordinary multiplication, but if you consider the other multiplication, that is Schur-Hadamard product, then you have a kind of duality. That is, the adjacency matrices with respect to entry-wise product behaves almost like primitive idempotent. That is, the primitive idempotents behave like the adjacency matrix with respect to Schur-Hadamard product. And the matrix P transforms adjacency matrix to EI, or express AI in terms of EI. So its inverse matrix will express primitive idempotence in terms of adjacency matrix. But then if you observe this, then you have two multiplication, two bases, and also in the definition of association scheme, we have an intersection number. That is the adjacency matrices multiplied with respect to this multiplication. Then you realize that there is one missing piece, that this matrices multiplied with respect to this multiplication we haven't considered yet. So that's what we are going to consider next. So adjacency matrices behave very nicely with respect to Shor-Hadamard product, and the primitive idempotency behave very nicely with respect to the ordinary matrix product, and the adjacency matrix expands in terms of intersection numbers. But we haven't discussed how the primitive idempotents behave with respect to Shor-Hadamard product. It should be expressible in terms of primitive idempotence again, because it's the basis, and this is again an element of the adjacency algebra, because the adjacency algebra is closed under the Shor-Hadamard product because of this property. So there must be some constant, just like Pijk, which express this Shor-Hadamard product of primitive idempotence. So that is called the crime parameter. But before doing that, let me first explain the second eigenmatrix, which is essentially the inverse of the P, the matrix P, which is called the first eigenmatrix. Okay, so earlier I have expressed the adjacency matrix in terms of primitive idempotence. So originally I had P here, but I can multiply the inverse of P to get P here. But for just the sake of normalization, we don't define P inverse to be Q, but the scaled version of the matrix P inverse to be denoted by Q. So Q is essentially P inverse except this scalar omega. So actually P times Q is the size of omega times identity. This is nicer because in this way the matrices P and Q behave quite similarly, and in some association scheme these two matrices actually coincide. Not always, but for some cases they are identical. So this equation means that if you look at the J component, that is EJ is expressed in terms of linear combination of adjacency matrices with coefficients are extracted from J's column of Q. So this is Qij, and with this scalar. Now, if I perform the entry-wise multiplication, then because they behave very nicely, so this AI, so if you multiply them together by Shor-Hadamard product, because of this, you just multiply component-wise, or the coefficient-wise this matrix. So it's immediate to express what happens to this Shor-Hadamard product to the primitive idempotence if you express in terms of adjacency. It's just the coefficients are multiplied. So the Shor-Hadamard multiplication in the adjacency algebra is nothing but the entry-wise product of the column vector Q, well, up to some scalar. Yeah, because we have scalar here. So there are two multiplications in the adjacency algebra, but because of the matrices P and Q, they can be understood very easily as the entry-wise product of vectors. So there is nothing very special about the abstract structure of these algebra, because they are just realized by entry-wise product of vectors, so they are abstractly isomorphic to the copies of the complex number. So here is the definition of the so-called crime parameters. as I said, you can express the Shor-Hadamard product of primitive idempotence as a linear combination of primitive idempotence. Because the primitive idempotence is the basis of the adjacency algebra, and this belongs to adjacency algebra. These numbers are called prime parameters. This is quite similar to the intersection numbers, which express the product of adjacency matrices in terms of adjacency matrices. Intersection numbers are by definition non-negative integers, but these prime parameters are not necessarily integers, and even not necessarily rational either. It could be irrational. But I will show you that they are non-negative real numbers. That is not difficult to show, so I will show you in this slide. But to do that, I need to know a very basic fact about the positive semi-definite matrices. So we know in the previous lecture, not previous, just a few minutes ago, I showed that these primitive idempotents are permission matrices. And this, of course, this is squares itself because it's an idempotent. So the eigenvalues are just 0 and 1. Of course, it comes from the diagonal 0, 1 matrix sandwiched by the unitary matrix. So the eigenvalues are 0, 1. So all eigenvalues are non-negative, and it is a Hermitian, so it is positive semi-definite matrix. And this curly inequality is the shorthand notation for positive semi-definiteness of the matrix. So the primitive idempotence EI is positive semi-definite. Now then, how do I prove that these coefficients are non-negative? Well, we just have to show that the left-hand side is positive semi-definite. But it turns out that is quite immediate, because if you have two positive semi-definite matrices, then their Kronecker product is also positive semi-definite. Because in the Kronecker product, the eigenvalues are just the products of the eigenvalues of each matrices. So they are, again, not negative. But then, what's the relationship between this Kronecker product and the Shor-Hadamard product? Shor-Hadamard products are obtained by entry-wise multiplication, but the Kronecker product is also obtained by entry-wise multiplication, but the only difference is that this matrix is much bigger because you consider all possible entry-wise multiplication. Here you consider only entry-wise product of corresponding entries. So that translates the fact that this small metric is a principal submatrix of the big matrix, and the principal submatrix of a positive semi-definite matrix is obviously positive semi-definite. So that gives positive semi-definite this matrix. Now this is expanded in this form, so, well, this is a positive scale, so we can ignore that. This linear combination is positive semi-definite. But in fact, we know all positive semi-definite matrices in the adjacency algebra. Well, you have suppose you have a Hermitian matrix in the adjacency algebra and express it as a linear combination of primitive idempotence. Then you ask yourself, when is it Hermitian and positive semi-definite? It's quite easy to see that this coefficient has to be non-negative. Because this EK just project onto some subspaces, and if you restrict this matrix to subspace, it has to be non-positive semi-definite, so this coefficient has to be positive semi-definite, and converse is also quite obvious. So those coefficients has to be positive semi-definite. So this proves the inequality that the prime parameters are negative. Now, this can be used to understand the spherical representational association scheme. A few days ago, we have a talk by Da Cao about association scheme. He mentioned spherical representation. But I vaguely define what the representation mean in mathematics. A representation is a description of a typical object in some category, or I'm not sure the association scheme can be considered as a category in our context, but the group representation is a homomorphism into typical object, like symmetric group or general linear group, and representation of algebra is a homomorphism into the typical object, the typical algebra that is matrix algebra. But then what is the typical association scheme? We don't have, we only give some example of association scheme, but that's not considered typical. But typical object which should be bigger enough to express almost every association scheme. That is the sphere. Well, strictly speaking, because we have confined ourselves in the definition of association scheme to be a finite set, sphere is not considered to be an association scheme. But in the reason, if you just relax the axiom, and you will immediately see that the sphere, you have an angular distance or Euclidean distance or whatever distance, you have a metric. The sphere is a metric space, so the distance, it defines a relation of pairs of points, and that could be considered as association. In fact, there's an orthogonal group acting on the sphere, so you may think of two orbits of the orthogonal group. So in this way, it's an infinite association scheme. So that's the place where we want to represent association scheme. So a representation of association scheme is a mapping from the set, underlying set, to the unit sphere, which preserves the structure of the association scheme. What does it mean by preserving the structure? Association scheme has a set of relations, and we want the pair in the same relation to be belong to the same pair, relation. That is, the relation in the sphere is defined in terms of the, say, cosine of the angle, which is same as the inner product. So it means this mapping is a representation whenever the image of a pair, alpha beta, in a fixed relation depends the inner product depends only on the relation. So this angle depends only on this relation. Well, it might be too abstract, so let me give you the very natural example of hypercube. Hypercube is also an example of association scheme. But the hypercube itself is a subset of the sphere. Hypercube, in this notation, it is the set of all sequence of length m, whose entries are plus minus 1, but I need to divide by square root of m so that it becomes a unit vector. So this is just a canonical standard way of embedding hypercube in the unit sphere. And if you restrict the distance function of the sphere to this hypercube, you have several distance, or in fact the distance, there are precisely m plus 1 values of distance from 0 to the largest. And these different values of distance can be expressed in terms of Euclidean distance, or angular distance, or the Hamming distance. Hamming distance measures or count the number of coordinates which are different. That's the standard way to define the metric in the hypercube. And because this here you can see that this is itself defines association scheme, but itself already contains the sphere. So you may think of this itself is a representation or spherical representation of association scheme. So this is an example of a spherical representation of associations. So now if you consider, if you are given an association scheme and try to embed the set of points to a sphere, then how can we do that? Okay, the embedding, well, realizing the set of points in a sphere is same as the giving the gram matrix. Well, of course, if you have an embedding, then you may compute the gram matrix. That is the table of inner product values of the images. So you have a matrix indexed by alpha beta of the underlying set of the association scheme. And the entries are inner product of the images of the unit vector in the sphere. So this is a matrix, square matrix, indexed by the underlying set omega of the association scheme, whose alpha beta entry is the inner product of phi alpha phi beta, and the values are certainly inner product of unit vector, so it's something between -1 and 1, so it has a real entry. But the fact that this is a representation means that this value depends only on the relation. That is, this matrix is a linear combination of adjacency matrices. So this matrix itself belongs to the adjacency algebra. This inner product is constant on the relation. It is expressed as a linear combination of adjacency matrices. Yeah? Of course, that is true if you are given a representation. But conversely, if you are given a matrix in this real symmetric matrix in the adjacency algebra, which is positive semi-definite, and diagonals are 1, then it could be a candidate of a spherical representation. But in fact, it is a spherical representation because there is a standard fact in linear algebra called the Cholesky decomposition of a positive semi-definite symmetric matrix. If you have a positive semi-definite symmetric matrix, you can express the matrix in this form, a rectangular matrix and rectangular matrix, and this is a transpose of this. This is some matrix H and the some matrix H transpose, and that is that matrix F, where this is F is bigger. This matrix F is bigger. So this big matrix may have smaller rank, and the rank is this small this small size of this smaller side of this matrix, and this is called the Cholesky decomposition, and it is so always possible for symmetric positive semi-definite matrix, and those those vectors gives a spherical representation. So the spherical representation of association scheme is same as finding the set of all symmetric positive semi-definite matrix and normalize the diagonal to be 1. But we already know, we'd already determined that when an element in the adjacent algebra to be positive semi-definite, yeah? Well, that is the question we could ask. In some sense, we already answered in the previous slide when I proved the crime parameters are not negative. Yeah. Okay. So what are the real symmetric matrices? Of course, the non-negative linear combination of primitive idempotency, but there is slight difference just that you have to keep in mind that we are concerned with the real matrix, while adjacency algebra is over the complex numbers. So the primitive idempotency permission but they may contain imaginary entities. So the primitive idempotencies are not suitable for spherical representation in the real Euclidean space. So what are the positive semi-definite matrices? I mean, positive semi-definite symmetric real matrices in the adjacency algebra. Of course, we have to have a positive semi-definiteness, so the coefficient has to be non-negative, but we need to require that they are real symmetric. But that's not difficult to impose, because it is a star algebra, so it is closed under transposition. Well, I didn't say how this transposition works, but the transposition gives a permutation of adjacency matrices, and it also gives a permutation of primitive idempotents. I said that these primitive idempotents are Hermitian, so if you take a star, then it doesn't give any, it results in a trivial permutation, but the transpose could give a non-trivial permutation. So I denote these two permutations, possibly different. Well, of course, it depends on the numbering, so it can be different. And this permutation by prime and the other permutation by hat. So you can group them together to get the symmetric matrices. So it means that if you are concerned with this real symmetric matrices, you might want to group those together. That is, in general, each adjacency matrix may not be symmetric, but you just consider union of the relation with its transpose. Then you may have fewer number of relations, but certainly you have a set of relations. Sorry, I shouldn't have an A. I mean, there's another set of relations, so without A. So this is, but if you take A and take a linear combination, you get the symmetric part of this algebra, and that is exactly what we want. It turns out that it results in a new association scheme. If you start with a commutative association scheme, it is called a symmetrization. So we are mixing the notation that A shouldn't be here. So you just take the union of all relations. If R is already symmetric, this is just R union R transpose is nothing but R. But if R is not symmetric, then R and R transpose are disjoint, and the union forms another relation which is symmetric, and you collect them all, then you get a partition, which is a coarser partition than the original association scheme, and it is called a symmetrization. It turns out this is another association scheme. The only non-trivial part is that it is closed under multiplication, but it's not difficult to check that it is closed. So it is a new association scheme. So, well, of course, it is natural to consider this symmetric association scheme if you are concerned with spherical representation, because sphere, the relation is symmetric because it's defined in terms of distance. So the corresponding idempotents are also easy to describe because you just consider symmetric idempotents. If an idempotent is not symmetric, then you have another idempotent which is different and so orthogonal. The transpose of that idempotent is one of the other idempotents. So take the sum, you get idempotent. Sum of two different primitive idempotent is another idempotent. So that gives another basis of the symmetrization. So the symmetrization is easy to describe in terms of adjacency matrices and also in terms of primitive idempotents. So let us look at the circle representation of the Johnson scheme. This is Johnson scheme which I mentioned at the end of the previous lecture. It consists of two element sets of an element, n element sets, and the relations are defined in this way. R1 is a pair of two-element sets that intersect at a single point, R2 consists of disjoint pairs. Well, you can use in the same way the unit vector in n-dimensional space, where n is exactly the same as this n. So each numbers between 1 and n correspond to the unit vector in the n-dimensional Euclidean space. So if you take two vectors and divide by square root of n, you get a vector of length 1, so which that lies in the unit sphere. And you may think of this as a set ij. So this gives a mapping from the underlying set of the Johnson scheme to the sphere, and the inner product precisely corresponds to these three different relations. Yeah? That is, the angular distance is 0 if you have the same pair, and it's easy to see that the angular, our cosine is 1/2, so the angular distance is pi over 3, and if you have a disjoint pair, they are orthogonal, so they form the angle, they form the right angle. Now, the theory I developed in the previous slide says that this has to be realized by the linear combination of adjacent symmetrics or linear combination of the primitive idempotence, because this grand matrix belongs to the adjacency algebra. Indeed, if you calculate what the entries of the primitive idempotence, then this grand matrix is exactly this one. Well, I didn't specify what E1 was, but in the program session, I mentioned how you get E1. And we also, Dazhao correctly answered in the program session last night that the rank of E1 is n minus 1. And the rank of E0 is, by convention, 1, that is the O1 matrix. So the rank of this matrix is 1 plus n minus 1, which is the n. So it certainly spans this Euclidean space. So that's the representation of the Johnsons. Okay. There's one important relation for the matrices P and Q. That is this relation. Well, P and Q are the two base change metrics which are essentially inverse to each other. So once you know P, you can invert P to get Q. But there is a shortcut to get the entry of Q. That is Qij, of course, it's essentially inverse, but you don't have to compute the inverse metrics. You can just directly rid off the Qij by transposing P and conjugate and then normalize by these positive integers. So let's see why this is the case. So by definition, P is the base change matrix of this way, and you invert this and scale it, you get the matrix Q. But how could these, the entries of these two matrices related? Okay, so for this K is the row sum of AI. So if you multiply 0, 1 matrix by the AI by the O1 matrix, then you get the row sum Ki. This is the constant. It doesn't depend on the row, and so it is a row. So it is denoted by Ki. J is up to scalar, same as the zeros idempotence, so you have the same equality if we replace J by 0. And this means that if you expand AI in terms of primitive idempotence, then this number Ki is the one of the expansion coefficient, that is the zeroth expansion coefficient of the ith adjacency matrix. So it is a 0i entry of this matrix P. So Ki appears in the 0i entry of matrix P. And I define this mj to be the rank of mj. So this is mj. Now, to get this identity, I just compute trace of this matrix in two different ways. Trace of AI times ej bar in two different ways. In the end, you get two different expressions, and if you compare these, this omega will disappear. You compare them, you get this equation, this equality. So let's see, first this is ej bar, but ej is a permission matrix, so bar is same as transpose. But if you think about what this trace of one matrix times the other matrix transpose, then it is just the sum of all entries of the product. That is also known as the Hilbert-Schmidt inner product if you have a star instead of transpose. But anyway, so this is the sum of all entry-wise product, sum of all entry of the entry-wise product. But then AI has 0 and 1, so it doesn't have very much effect on multiplying AI by entry-wise product. But but this can be easily computed by the expanding EJ in terms of adjacency metrics, because EJ is a linear combination of adjacency metrics with coefficient given by Q. And with respect to this Permutation inner product, with respect to with respect to this the Shor-Harama product, the entry-wise product of AI just extracts the coefficients of EJ, that is Q or IJ. And then you have to count the number of occurrences here, but the number of occurrences is the number of ones in this matrix, which is because each row you have ki ones, and so the total number of the row is this one. Then the bottom omega comes from this omega, and so omega cancels out. And in the second way, you just take this bar outside the trace, and then trace, but this is just the usual product. To get the usual product, you expand AI in terms of primitive item points, but then you have a coefficient PJI. But PJI is a scalar, so you can take out the trace and you get this expression. So you have some relation between this eigenmatrix P and Q. This relation can be used to derive the south part. This is a nice application of theory of association speed. It gives the upper bound on the size of a clique, defined clearly in a graph defined by the adjacency relation, say, for the R1. It doesn't have to be particular one. You just take a relation and call it R1, but we don't want a directed one, so we just a symmetric one and non-identity relation. And suppose that graph has a clique of size C. Okay, then denote by the unit vector, the characteristic vector of that clique, U. Then it has C ones, so the inner product is just C, and this counts the number of edges in the subgraph corresponding to C, so there are C times C minus 1 ordered pair of adjacent vertices, and the rest is 0 because it is a clique, so no other relation appears in the clique. And if you just compute this, if you just use this vector and compute this product, remember this E1 is one of the in fact, an arbitrary idempotent of the adjacency algebra. So it is non-positive semi-definite, so it is non-negative. So you write this E1 as a linear combination of adjacency matrices, but you lose almost all terms because this is 0 for except I equals 0, 1. So you just have two terms in this sum. That is that 0th term and first term. The 0th term is just C. This first term is just C times C minus 1. So you can factor C out and use this Q11 to express it in terms of P. And this Q01, it turns out this is just a rank of the idempotent, so it's M1. So you get this inequality. So you can solve this inequality for C. Well, it is not possible at the first glance because you don't know whether P11 is positive or negative. But if P11 is positive, you don't get any information, so you might as well assume that P11 is negative. In fact, there are such P11 if you choose the idempotents appropriately. So it means, and also if you notice, the P11 is the eigenvalue of the first adjacency matrix, then you may as well write this as a theta with the eigenvalue, and the inequality is optimized if you take the smallest eigenvalue. It gives the strongest inequality if you minimize P11 negative. So this is the bound for clique in a graph defined by an association scheme. Okay, so that's the last slide, but it's just a collection of summaries, so I don't think I need to spend any time on showing summary. So thank you very much.
Would there be
Questions? Yes?
in the eigenvalue bound with a minus sign?
Oh, we have minus sign. So there's something wrong here?
Yeah, there's a minus.
Yes. Otherwise, yeah, I have a critical side less than 1. Yeah, that is calculated. Sorry, thank you. Yeah, so this is really minus. Thank you.
Any other comments? Well, thank you very much, and we're looking forward to
Thank you.